Alright, so welcome in this new video. So here we are continuing to look at the expression for the hypervolume of a ball in k dimensions and with the ball having radius r. Now in the previous video what we looked at was essentially what would be a pedestrian strategy to do it in, let's say, Cartesian coordinates, and I've simply illustrated how it would go in 3 dimensions, and essentially in 3D we already see that, yeah, I mean, this can be done in some sense relatively easily. However, this is relatively tedious, and if you imagine to do it in 1000 dimensions, then somehow you need to find a way to make it a bit faster, and it was not obvious how we were going to find a general expression for the Cartesian expression. Now, I'm not saying that there is not a way of doing it in the Cartesian with the Cartesian method. However, usually the goal was to show it's not convenient. So what I'm going to show here is one particular trick that relies on some preliminary knowledge. So here we need to put it forward. I just want to mention there is another strategy which is based on recurrence relations. So you can find a relation between the integral in k, the volume in k dimensions, and k minus 1 dimensions, and then with this recurrence relation you can solve it. You can get basically some kind of equation and solve this equation, and in the end this all goes well. Okay, but in this case I'm not going to rely on such things. I'm going to rely on two things mostly. So the first piece of knowledge that I want to rely on is Gaussian integral. So that's the integral from minus infinity to plus infinity dx exponential minus x squared is equal to pi to the power half. Okay, so that's the first preliminary knowledge. This can be found out in various ways, but at least that's where I want to start with. Okay, I'm not going to prove this. There are many ways to do so, but this is not part of this thing. The second thing is that the surface, okay, of a hypervolume of a k-dimensional ball okay, is expressed. So what I mean here is the area, rather, so the area of the surface of that k-dimensional ball would be something like S. So that's the surface of the k, so I will call it Sk of R, and that would be omega k, and then R to the power k minus 1. Okay, and that's important here because so r to the k minus 1 comes from the fact that obviously the surface of a ball has one length less, if you will, than the ball itself. And here there is a very important term which is called the solid angle, okay, in k dimensions. Okay, now to be honest, I won't go too much in details here. That's the definition, if you will, of the solid angle, which is that the surface of a sphere in k dimensions will actually be omega k times r to the k minus 1. So that would be the total solid angle of a sphere in k dimensions. Okay, so you could take that as, in some sense, a definition of the total solid angle. Okay, now once this is said, then we can also notice, that's part of this preliminary knowledge, that that essentially if I have Sk r dr, then this represents a hyperspherical shell. Okay, in k dimensions. Okay, so essentially you will have something like this, and this would be r, and here you put some dr here, so that would be dr, and you get a shell. And what you can do then, it integrates the remaining volume. Okay, you know the surface, you know the width. You can integrate this over R by adding up the volume of concentric shells. Okay, and so what you can get is that Vk, there is a relation between Vk and Sk, is that Vk of R is equal to the integral from 0 to R, and then here I would put some dr like this, okay, so that there is no confusion, of omega k, and then R to the k minus 1, R to the k minus 1, and that's it. That's it. I'm basically adding up the volume of concentric spherical shells in k dimensions. Okay. Now, what does that give you? Well, that gives you omega k over k, and then R to the k. Okay, so the reason why this is interesting here is because this relates, this gives some kind of generic expression for the volume of a sphere in k dimensions. Okay, so there is omega k is a solid angle over k. Okay, and that roughly that's it. Okay, so what I'm going to do next is, so of course I say it's a quick trick. It's a quick trick if these things are kind of known, and then it takes again kind of a couple of lines still to work it out. So here what I'm going to do is introduce an integral ik, which is the following. So this is the integral from from minus infinity to plus infinity dx1 exponential minus x1 squared, then minus infinity plus infinity dx2 exponential minus x2 squared, and then you probably get where this is going, integral minus infinity plus infinity dxk exponential minus xk squared. Okay, so that's basically what I'm going to calculate. Now this is obviously an integral, a Gaussian integral to the power k. So I know the value of this integral. This is pi to the power k over 2. So it's really easy to calculate this integral. However, I also know that this integral is minus infinity plus infinity, minus infinity plus infinity. So here I've got k integrals. Okay, and then here I've got dx1 dxk, all right, and then exponential minus, and then the sum for, let's say, I that ranges from 1 to k, xi squared. All right, so that's basically what I've got. Now what I'm going to do here is basically go into spherical coordinates, or a form of spherical coordinates. So in spherical coordinates, what we do is that we define so basically spherical coordinates, so what I'm saying is that I will get that the sum of this squared is by definition then turned into a variable, a radius variable, which is called r, and it is r squared. Okay, so that's the definition for the radius variable, and then I will the measure element dx1 dxk in generalized spherical coordinate system becomes something that will read like this: d omega k then I've got then I've got r to the k minus 1 dr. Okay, so again, that's a general measure. So here, this thing here would be the elementary solid angle in k dimension. Okay, so that's how that works. Again, this is just generalizing a little bit the things I've said before, but once I've put it this way, then what I get is that ik is equal, can be written as minus infinity. So first I need to, in fact, it's not like this actually, that would be 0 to plus infinity dr. Then I've got r to the k minus 1, okay, and then what I have is that I've got this exponential minus r squared. So exponential minus r squared only depends on r, and then within the elementary solid angle I've got plenty of variables, okay, but the point of the solid angle is that all the length related aspect has been removed from it, and therefore it can be integrated separately. Okay, so d omega k, which has to be integrated separately, and d omega k here I have to say over total solid angle. Okay, total solid angle, and that's it. So that's how it reads. Now the integral of d omega k over the total solid angle is just omega k itself. Okay, so that would be just omega k, and then integral 0 plus infinity dr r to the k minus 1 exponential minus r squared. Okay, so I'm almost kind of there here. What I need to do, you could say, well, okay, that's fine, but you need to know that what I'm trying to do is actually finding omega k, because what I've shown before is that if I know omega k, in fact, then I'm done. I actually know the volume of a sphere. So here in this particular case, I'm trying to find omega k, so I need to find a way to formulate this particular integral slightly differently. So the way we can do that here is simply by putting u is equal to r squared, and if I put u is equal to r squared, I will get so let's not get ahead of ourselves. That would be r is equal to u to the half. Then I would get dr is equal to a half, and then du u to the power minus a half. Okay, and also I need then to replace all the things kind of together. So let's find out what we get. So we get that ik will be equal to omega k, and then here that's the integral from 0 to plus infinity. So here again, let's be careful when I replace all these things. So dr has to be replaced by, so let's put du, then I've got half that comes in, then I've got u to the power minus a half, and then u to the power minus a half, but to the power k minus 1, okay, and then exponential minus u. Okay, so in the end I get this is omega k, then I've got this factor half, then 0 plus infinity, and then I've got du, and let's see how that goes. So I've got u to the power minus a half, and u to the power minus, and then so I'm just trying to find out where I could have gone wrong. yeah, sorry, I need to replace r here, so that's u to the power, so here is plus half, sorry, so it's u to the power k minus 1 and then over 2. Okay, so what does that give us? Essentially that gives us k over 2 minus 1, so exponential minus u, so that gives us omega k over 2 integral 0 plus infinity du, and then I've got u to the power k over 2 minus 1 exponential minus u. And so this is actually, so then half omega k, and this is the Euler gamma function of k over 2. Okay, so that's what it is. So then I'm almost done here. I've got essentially that in some sense I've got pi k over 2 is equal to omega k over 2, and there I've got gamma of k over 2. Okay, so I'm almost done. So I get that therefore omega k is equal to 2 over gamma k over 2 times pi to the k over 2. Alright, so you see, just by using this, now of course the Euler gamma function is something that you need to know as well, but in any case that's what it gives. That's the definition, basically, that I used. And in the end I replaced, therefore, in the expression from before we had vk of r, which was omega k over k, if you remember, and then r to the power k. Okay, so I replace. This is equal to 2 over k pi over pi k 2, and then gamma k over 2, and then r to the k. Now I'm using a property of the gamma function. So there is a property that says that gamma of x plus 1 is equal to x gamma x. Okay, and that's because essentially that's a generalization of the factorial function. So that's what this is, and I can use that to get the general expression, which is worth writing in red, which is vk of r. So in any k dimension with any radius r would be pi k over 2 divided by gamma k over 2 plus 1, and then r to the k, and that's it, you're done. So if you actually, if you know the definition of the Euler gamma function, and you have an understanding of how the volume of a sphere depends on r, it's basically that's what matters, how it depends on r, then essentially you're kind of set to find out this particular expression. So that's it. I hope you enjoyed this part. I always love this particular trick where you start like totally out there calculating Gaussian integrals, and eventually you end up with calculating the hypervolume of a sphere.